Well, we're going to talk about aromatic compounds, okay? Right, they originally were called aromatic compounds because they smelled good. As maybe you know now from organic chemistry, not everything that's aromatic actually smells good. Aromatic compounds are generally known as arenes, and they contain conjugated double bonds. And it turns out if the double bonds follow certain criteria, there's incredible stability in this conjugation, more so than you just expect for regular conjugated bonds. Okay, I'm going to skip some of these lovely things. Oh, yeah. Actually, in large, like natural products and large molecules, often there are regions that are conjugated. So you'll notice this is a aromatic. This is an aromatic region. This is another aromatic region. They're isolated from each other sometimes. Like this has a couple of sp3 carbons in between. And sometimes they can conjugate to each other. So if there was another carbon and another double bond in here, you could actually have this system conjugated to another one. Okay, all those things affect the stability. Okay, so we're going to be just talking about mostly benzene in this chapter. And generally speaking, many of the compounds have names that you would expect if benzene was the parent. So this is chlorobenzene, that's a nitrobenzene, ethylbenzene. So the nomenclature is fairly simple, okay? But there are a couple, well, maybe there's more than a couple, where benzene is part of the structure, okay? But adding a substituent gives it a new parent name. So for example, toluene is benzene with a methyl group. Phenol, which you've encountered in an earlier chapter, is a benzene with a hydroxy group on it. Anisole, which is the one you should have been simulating the other day for the lab. That's due today, right? That's a methoxybenzene, sometimes called methoxybenzene. Aniline is with an NH2, benzoic acid, benzaldehyde, acetophenone, and styrene. These are all actually names you need to know. Okay? So, if I made a molecule that looks like this, I'm just going to make something up here. OCH3. So that's anisole, right? And then I put an alkyl group on it, like that. So the parent for this would be this. Can't get my pen to write. Okay. And this would be the substituent, so this would be ethyl. When you number it on the parent, whatever the substituent is that gives the benzene its name, the ring structure its name, is the number one carbon. Okay? So we have 1, 2, 3, 4, 5, and 6. You number it in the direction that gives you the substituent the lowest number, like you would expect. So this would just be 3-ethyl anisole. Okay. What if there was a substituent on 3 and 5? So let's say I did it like this. I'm going to use NH2, so this is aniline. By the way, the conjugated system on the inside is often drawn as a circle. Okay, so the parent in this one is this. That's aniline. Ay, ay, ay. Okay, so aniline, that's a methyl group on the left. So which way do you number it? Alphabetically, yeah, so E first. So same way in this case. 1, 2, 3, 4, 5, 6. So it would be 3 ethyl. So nothing crazy. 5 methyl. Aniline. Aniline. There you go. Ah, it's writing again. Good. Questions? It's pretty straightforward. We'll deal with like 2 functional groups in the next chapter. So. Okay, so now benzene can also be a substituent, and if it is, it's called a phenyl group. Okay. And it's often abbreviated pH, or can be abbreviated as phi. This is the Greek lowercase p, I guess. I don't know, phi, whatever phi is. Maybe it's an F. All right. So 1-phenylheptane would be the name for that first compound. I'm not sure. That would be tetraphenyl. What is that name of that thing? I don't remember the name of that one. But that would be a tetraphenyl. That's would be the name for the substituents. Okay. Now, one other thing to recognize on benzene, so I'm going to go back to the ones I was just drawing. Okay. If you have 2 substituents, and this only works for 2 substituents, so let's say it's like this. Each of these positions that I'm drawing has a different letter name. Okay, so we've learned some of these. So let me draw some of these. We're going to do CH3 here. So this would be ortho, methyl, anisole. If it's in the 1 and the 4 position, or the 1 and the 3, this one is meta, and then 1 and 4. Now 1 and 4 could be drawn like this, so I'm going to draw it a little different. That's para. So O stands for ortho, M stands for meta, and P stands for para. And para is 1,4, can be called 1,4 or para. Meta could be called 1,3 and meta, and ortho could be called 1,2. Okay. What's that? Any kind of substituents, and there's only 2. Okay. If you have 3, you just have to use numbers. It's just because there's a lot of really common 2-substituent aromatics, benzene rings. Okay, so one of the common disubstituted benzene rings are known as xylenes. So xylene, in general, like if you get rid of the ortho, meta, and para, just means benzene with 2 methyl groups on it. Okay. Orthoxylene has the 2 groups next to each other. Metaxylene has it in the 1 and the 3. And paraxylene has it in 1 and 4. So like in the experiment you guys are doing this week, all 3 of those are potential reactants for that experiment. Okay. So like I said, benzene could be the parent, or benzene could be the substituent. The general rule is the longest consecutive chain of carbons is the parent. If there's a tie, we usually attribute the parent to the ring. Okay? So this is the rules. I'm going to skip some of this since we've talked about it. But the only rule we really didn't talk about is what do you do if there's a ring and a chain? And so if it's whichever one's longer is the parent. If there's tie, goes to the ring. That's the same rule we used like when was that? First semester somewhere a long time ago. Yeah. Okay, so let's name this. Right, parent, probably going to be the aromatic ring. So you have to go back and look to see what is this called. And you guys should know this one already because it was from the alcohols chapter. As a hint. Phenol, yeah? Oh, shoot. If that makes sense to you, that's a phenyl alcohol now, right? That's where it gets its name. And phenyl is the substituent name for benzene. And then we have to number it. Now there's 3 substituents on the ring, so we can't use ortho, meta, and para, so we have to use numbers. The 1 goes with the alcohol functional group because it's part of the phenol. So I have 3, 5, dibromo, phenol. Okay, let's do this one. So we're gonna let's use ortho, meta, and para. Okay. So go back and look. Oh, did you guys actually write these things down? I'll help you learn how to remember some of these names. Some you won't. What kind of functional group is that? So this is benzaldehyde. Okay. So this parent, benzaldehyde. So there's 2 acceptable names for this, right? This is 1 and this is 4, or what's the other designation? What's that? P, yeah? So P chloro. Sorry, I have to write really slow or it doesn't track. Or it could be 1,4, or sorry, it could be 4 chloro, right? You know, I don't have a good way to remember that one, but that's called toluene. So it would just be M-bromo or 3-bromo, okay, toluene. So I'll just put the first part of the name underneath it, if I could get it to track my pen. And what is this? This could actually have 2 different names. We'll treat the nitro group like we did the others. Those are the substituents, okay? But this could also be called methoxynitrobenzene too. Okay, so there's other, like sometimes you can mix these things up and it's okay. But in this case, we'll treat the nitro as a substituent, okay? That's the parent. That one's known as anisole. Again, we did that earlier. So this one could be O-nitro or 2-nitro. So there's a funny story, I don't know how true it is, about the structure of benzene. Before they actually knew the structure of benzene, they had proposed a lot of different ones. Because there's double bonds here, like they figured out there could be possibly double bonds, what they propose is actually it's short on one side, and then the next side would be long, and one side would be short, and one side would be long. The shorter sides would be the sides with the pi bonds, and the longer sides would be the sides without the pi bonds. But when you actually analyze benzene, okay, all the sides are equal length. And actually, we didn't know that until the crystal structure was determined, like in the 1930s. And this was in the middle 1800s, okay? So there's a story associated with Kekulé. And if you remember, we might have covered a little bit about Kekulé drawings. They're basically Lewis-style drawings in the first semester. Kekulé supposedly, in a dream, right, saw a snake chasing its tail in a circle. And some of the stories say that he was on like morphine or opium at the time. And what he suggested from his dream, okay, is that these double bonds are going around in the circle like this. So that sometimes you can draw it like this. You notice that satisfies the Lewis structure for benzene, or it could be drawn like this, and this satisfies the Lewis structure for benzene. And that helps to explain, at least the movement of electrons in a circle helps to explain like why the sides are all equal sides. We kind of know, I think we kind of know, that each one of those is sp2 hybridized, and those electrons are delocalized in that ring anyways. So what Kekulé saw in his dream perhaps was the delocalization of the electrons as the snake going around the ring. Okay, or he was just on drugs. I don't know. I like the he was on drugs idea. I'm not suggesting you do that. And so sometimes when we draw benzene, we draw the circle like this. This is the resonance. It's, you know, why do we draw it like this? It's the resonance hybrid for these two structures if you were to draw where the electrons were going. Okay. Okay, so benzene turns out to be incredibly stable. If you take an alkene and you mix it with Br2 bromine, it's a very rapid reaction, happens at room temperature, and you end with the vicinal halides, the bromination product. Okay. If you do the same thing with bromine, there's no reaction. So the reason for that can be seen if you look at the heats of hydrogenation for benzene. Okay. If you look at one double bond and the heat of hydrogenation, this is the energy that you'd expect to get. So this represents, in essence, the energy of the molecule or the stability of the molecule. If you have two double bonds, right, you can get an energy of 232 kilojoules of energy released as you go to cyclohexane. If you just take these two numbers and you extrapolate them out, right, what you expect for three double bonds is 360 kilojoules of energy. Instead, what you get is that the aromatic ring, okay, only gives 208 kilojoules of energy, so it's about 152 kilojoules. It's got more, almost as much stability in it as it does instability. So if you're going to try, for example, to break one of these double bonds and go to a system that has two double bonds in it, right, you're going to have to overcome this stability energy from here to here. There's a lot of energy involved in just breaking open the benzene ring. This difference in energy that we get, oops, sorry. Is often known as resonance energy, or hang on. But is what we associate with the term aromaticity. It's that stabilization that you get above what you would predict from not having any delocalization at all. Okay. Why is that diagram off the bottom of the screen? I think somebody zoomed the projector, or maybe I just need to pull this down further. Oh, look, there's the bottom of the slide. Okay. Let me do this real quick. So, ignoring what's on the screen, because the screen is what we're going to go to first, or next. Sorry, we're going to do this first. Based on what we've talked about so far, right? There's 3 p orbitals in here, or 3 pi bonds in here. Each one of these has a p orbital associated with it. And what you can do is, on a first guess, based on what we learned already, if you were trying to draw the energy level diagrams, your first guess would be, well, it's like this. It's just 6 orbitals in a row going up. This would be psi 1, psi 2, psi 3, psi 4, psi 5, psi 6. There's 6 orbitals here because there were 6 atomic orbitals that go into it. If you were going to fill in, right, so there's 6 here, 6 AOs, 6 MOs. If you're going to fill the electrons in, right, how many electrons have to go into this system? How many double bonds are there? 3, right? Each double bond has 2 electrons. So you can go like this. Each pi bond goes like this, right? 1, 2. Now, we don't have the drawings, well, they're up here, but we don't have drawings to support this yet. But generally speaking, when it splits up like this, the lower half is bonding orbitals, and the upper half is the anti-bonding. So this is the anti-bonding, this is bonding. And one of the things that you could guess, like first off for benzene, is that benzene's really stable because it puts electrons in all the bonding orbitals, but there's no electrons in the anti-bonding orbitals. Okay? So benzene fills the bonding orbitals and doesn't put any electrons in the anti-bonding orbitals. It's okay to just say, call it ABOs. Okay, so that's a pretty good first guess. We know, actually, based on the kind of work that I did earlier where I drew the molecular orbitals, that the molecular orbitals actually look like this. This is the lowest energy molecular orbital. You notice how it's all red on the top and all blue at the bottom? That actually represents benzene when all the blue, they put red at the top. All the blues are at the bottom, like this. And all the reds are at the top. So this part makes a bonding part of the bonding molecular orbital, and this part makes part of the bonding molecular orbital. And when they merge together, it looks like a hamburger with a red and a blue bun, right? There's the top bun, there's the bottom bun. So it's literally hamburger bun shape. Except in benzene, the hamburger bun shape has a hole in the middle. So it's like a donut hamburger with no meat. Sorry, that was for you. Maybe bacon, just going around the edges. But that's what that is, and it has a little bit of a hole in the middle here. Okay, but then as you draw the different molecular orbitals, what we find is that there's two that are actually the same. There's this one, right, with the one node in the middle this way, and then there's this one with the one node in the middle this way. And so the diagram that I drew here is not quite right, because in linear systems, this is what you get, but in a closed ring system, sometimes you end up, as you're flipping the orbitals over, right, you end up with symmetries that make two orbitals the same. And that's just because it's a circle, and you can have a node in the middle this way and a node in the middle this way. And so what you end up with, instead of these two being different like they are in a linear system, they end up being like this. Same energy. But it's still true that these are bonding and these are anti-bonding. Okay. So that's the only difference. It happens because it's a ring instead of a linear molecule. And the ring causes these two to be exactly the same. And then the anti-bonding, it turns out mathematically those two turn out to be the same too, even though they don't look like it. And it's still true that when you fill the molecular orbital diagram, all the electrons go in here. So that's what they're showing in this diagram. Bonding molecular orbitals filled, anti-bonding molecular orbitals not filled. And so that helps us to explain this aromatic stability or aromaticity of the molecule. Okay? And that energy, again, is that difference in energy that we're seeing between the extrapolated 3 bonds versus what it actually is. Yeah, high-level mathematics, blah, blah, blah. It's actually based on symmetry. There's like a whole field of chemistry called group theory, which helps you to determine what the shapes of the orbitals actually are. And then the mathematical calculations help us fill it in. Okay. So it turns out if you measure the energies of different conjugated ring systems, okay, not all of them are aromatic. That is, not all of them have aromatic stability, okay? So 2 examples are cyclopentadiene and cyclooctatriene. If you try to brominate cyclooctatetraene, it's very easy to brominate it. Okay. And this is another weird reaction I will not go into, but this is one of these concerted pericyclic reactions, right? Where you take 2 cyclopentadienes and they form cyclooctatetraene. Okay. So why don't they show stability? And part of it comes when you draw the molecular orbitals for these things. So, let me do this. Again, here's a cyclopentadiene, right? How many p orbitals? 4, because there's 2 pi bonds, right? So each pi bond's 2 p orbitals. So if you were just like first guess, if it was a linear molecule, how many molecular orbitals do you predict? If there's 4 p orbitals, 4 AOs, how many MOs do you expect? Right, what did we do here? Well, there were 6 here, and you end up with 6, right? So if it was a linear molecule, you would automatically assume that there's 4. This is actually, this principle is called conservation of orbitals. I don't know how they came up with it. I've totally forgotten that little detail. But I remember if I have as many atomic orbitals that go into the system, they end up as molecular orbitals. So I'll get 4 MOs. And that's how you would think it would be if the molecule is linear. It turns out when the molecule is cyclical, that what ends up happening is you get this. And this is a bonding, this is an anti-bonding, and these are non-bonding. If you remember non-bonding orbitals, they are the same energy as the p orbitals that they were made from. So if you put the electrons in this system, right, how many electrons go in there? 4? 4. It's 4. Because you got 2 double bonds, 4 electrons, right? 2 pi bonds, 4 electrons. 2 double bonds is actually 8 electrons. But so the 2 pi bonds, right? 4 electrons, because we're just doing the p orbitals, they actually go in like this. So here's the thing, right? These give stability to the molecule so you can form it. These don't help at all. They're not paired, right? And so actually, they only get stability from 2 electrons and not all 4. Whereas in benzene, because of the symmetry of the molecule, 6 electrons go into giving the molecule stability. So these orbitals, because these electrons are unpaired, what you guys remember from like Chem 1A when you did orbital diagrams, right? Pairing electrons makes them more stable. These are actually less stable. And so they turn out to be what we call anti-aromatic. This molecule is a lot less stable than you predict because you're sticking in unpaired electrons into non-bonding orbitals. Okay? Same thing happens, okay, in cyclooctatetraene. In that when you draw the orbital energy levels, right, tetraene, 4 times 2, 8 electrons, right? 2 go into the lowest bonding orbital. You guys know what that one looks like, right? That, again, this kind of looks like a donut with a hole, like a hamburger bun. All those things kind of merge together. Doesn't actually sound that appealing to me. But, and then there's, when you fill them up, 1, 2, 3, 4, 5, 6, then you have 2 unpaired electrons. So it, again, leads to instability in the molecule. In fact, it's so unstable to have the entire system conjugated that cyclooctatetraene usually folds up so it doesn't conjugate the entire system and actually forces isolation of the double bonds from one end of the molecule. It looks like this. So the pi bonding is not as efficient, and so it breaks that conjugation, so you end up having 2 different pi systems that aren't as unstable as having the 2 unpaired electrons in the middle. So it's a folded up molecule. Okay, I'm going to teach you something. Some rules. I don't know if I have the rules on a slide here or not. Yeah, so here are the rules, and then I'm going to draw something for you. It's called the frost circle. So, actually, next slide. Next slide. There's something called Huckle rules for aromaticity. Huckle sort of summarized all this stuff up so that it was easy to determine whether a system was aromatic, anti-aromatic, or none of the above. Okay? Remember, aromatic is a lot more stable than you expect. Anti-aromatic is a lot less stable than you expect. And then none of the above is just like it's just the stability that you expect. Right? So aromatic compounds, fully conjugated ring with overlapping p orbitals. So, fully conjugated. And I'm going to rephrase that last bit, flat, right? And the consequence of flat means p orbitals overlap. And then, right, he said it has an odd number of electron pairs. In the pi system. So you can see how benzene meets this criteria. So continuously, right, fully conjugated means continuously sp2 hybridized. That's these guys. These are all sp2. All right. So it's fully conjugated ring system. Okay. How many electron pairs? 1, 2, 3. 3 electron pairs. So based on that criteria, Huckle's rules say that that's an aromatic system. What about and if I say that's an aromatic system, what does that mean about its stability? Not just that it's really stable, it's a lot more stable than you predict it to be based on its structure. Okay? Because there's some things that you predict to be really unstable, but they're aromatic, so they're really more stable than you predict them to be unstable. I don't know if that makes sense. Here's one of them. Right, that's unstable. There's like no doubt about it. That's really unstable. It's a 3-membered ring with a carbocation, right? But if you look at the Huckle criteria, right? sp2. I didn't draw the hydrogen in, but there's clearly, it's carbocation, so it's missing something, right? And these are sp2. Okay, sp2, odd number, 1, right? 1 pair, so it's aromatic. Now, that is to say, it's a lot more stable than you predict it to be. It's still unstable. Like, if you threw that in a party, it would blow it up, right? An electron party, not a... And maybe you like that. I don't know. I'm the more stability benzene type. Some of you are probably more the cyclopentadiene ion type. Sorry. Tenium? Yeah. Okay, here's another one. I'm not going to put a charge here, but I want you to tell me what it needs to be. Now, right now it's like this. What version of that would be aromatic? So if I put a plus charge, let's try that. So it would be flat, it's continuously conjugated. How many electron pairs? Two. It's an even number, right? And what we find is those are actually the systems that are anti-aromatic. So it's like very unstable. How would I make it aromatic? Huh? Well, I can't remove a bond because that'll make it positive, right? So what I have to do is remove the atom and leave the electrons. So if I remove the atom, and do that, and give it a negative charge, okay. That, remember we talked about delocalization of electrons before, and if a pair of electrons can be involved in resonance, then it is involved in resonance. So this has a resonance structure which says that this can be involved, like that, and then the electrons go to here, and then what you end up with is like this. And I know it just looks like a twisted version of that, but it's the electrons moving around. That means that this is sp2 hybridized. Because it can be involved in resonance. So how many pairs of electrons involved in that system? 3 pairs, right? Because I have the lone pair, which is involved in resonance, and I have the 2 pi bonds that are already there. So this is aromatic. So this is an aromatic anion, this is an aromatic cation. It doesn't matter like charge, it just matters electrons. Okay? It would be anti-aromatic if you had fully conjugated overlapping p orbitals. That means ring flat, right? And it had an even number of electrons. So that's why this one is anti-aromatic. If I put a negative charge on here, then I would have 2 pairs of electrons. That would be anti-aromatic. Okay, questions about aromatic, anti-aromatic? You know how to see them? Yeah.
So, do these
Cyclopentadiene. Yeah.
Do they fold?
No, they don't. Wait. Like this?
Any of them?
No, because it's too small to be like out of the plane. Once you get to 8 carbons, that's when you start seeing them not be flat. If they can avoid being anti-aromatic and really unstable, that's when you see them start to fold up. Okay, what about this one? Continuously conjugated? Yes or no? Yes. Bold assertion. But yes, he is correct. Why? All right. Because every carbon is touching a double bond. Okay. So it's continuously conjugated. Now we have to count the electron pairs, right? So you go like this: 1, 2, 3, 4, 5, 6, 7, 8. Okay. So what do you guess? Yeah, you would guess that the whole thing is not aromatic. If it can leave this part out, then the external part is aromatic, right? But you would predict based on Huckle's rules that that's anti-aromatic. Okay, so here's the thing. In this molecule, because including the center bond in the delocalization makes it anti-aromatic, it doesn't actually conjugate that center double bond. And it leaves it isolated away, okay? I'm just telling you that, okay? So these electrons, these pi electrons around the outside are the part of the aromatic system. This actually helps to keep it flat, but those electrons don't delocalize, apparently, through the system. I know, but I thought I would point that out to you anyways. So this is kind of an interesting thing. How do you know? Remember I was drawing molecular orbital energy levels, and I was saying, oh, well, if it was linear, it'd be all in a row going straight up. But if it's a ring, then they're staggered in different shapes, right? So this guy, his name's Frost, which gives his rule a really cool name. It's called the Frost circle. Okay? He figured this out. He said mathematically, right, if you draw a circle and you inscribe the polygon of choice with the point going down, you got to draw polygons like really regularly or this doesn't work, okay? Then the energy levels for the molecular orbitals are drawn in such a way that at every joint, that's where an orbital exists. And so that's why, we're not going to use this that much, but I want you to know the rule. When you draw benzene, if you can draw it normally instead of like I am there, and that's inscribed on a circle, everywhere that thing crosses the circle, that's the molecular orbital energies for benzene. So it goes down to 4, it works great. There's the 4, and you can see if you have 4 that you have 2, right? You have a bonding, you have 2 non-bonding and a bonding, anti-bonding. You have 3 bonding and 2 anti-bonding, and then you have benzene, and so this shows the distribution of orbitals. Like I said, we're not going to use it that much. I just want you to understand what it is in case it comes up, like draw the Frost circle, like on your final exam kind of thing. You know, what is the Frost circle? How is it used? It's used to determine the energies of the molecular orbitals. But it's like anything else like this, it's just kind of like a trick, right? If you really need to know those energies, you throw them into a molecular modeling simulation, and it'll calculate the energies of the orbitals where you can actually draw the diagram from the simulation. Okay, let's see. I think that's all that we'll do for today. We'll move on from there. Oops. Next time.